The area under the curve, but the area bounded between the curve and the x-axis, which also tells us what, Caitlin? The total change or the total of something, right? Total amount, okay? Okay. I'm gonna skip through a few things here. Okay, so let's just look at this first example. We'll step through it. Okay. In order to avoid flood water entering your home, you rent a pump that can remove water at a rate of 500 gallons per hour. So we have a rate for the first 8 hours of pumping. As the storm grew stronger and got a second pump, and the next 16 hours, you could remove 900 gallons per hour with pump. Okay, so draw a graph that models the removal of stormwater from your property. Okay, so for the first 8 hours, right, we're removing water at a rate of, what was it again? 500 gallons per hour. So we're going to make this axis over here. This is our time. Time in hours. Okay. And then over here, this is going to be, does it give us a variable that we need to use? Okay, so we're going to call this just, we'll call it G of T. G of T. So this will be gallons of water. Okay. Bless you. Yeah. This is the Unit 6 notes that are in your Google Classroom. It just popped up. Okay. All right. So for the first 8 hours, we're removing 500 gallons per hour. How would I graph that? Oops. Caitlin.
From the origin, you go up, and once it hits 1, you're at the 500 mark, and then it'd be constant to 8.
So we're going to go up to 500 here, you mean?
Yeah.
So we have a horizontal line, right?
But didn't you have to start, you have to start at the origin, though, because it's, immediately not at 500? Because, once you hit the 1 hour mark, you're at 500, but before that, you wouldn't be at 500.
It does not. It doesn't say that. I know what you're saying. You're thinking from 0, it's going to take 1 hour to get to the 500 gallons per, but it doesn't say that, right? It just says that it's for the first 8 hours. So yeah, it doesn't say that it takes time to build up to that. Okay. Okay, and then when we add the second pump, we're now pumping at 900 gallons per hour. So we're going to go up here to 900, and we'll go over to, oops, for how many hours? 16 hours, right? Over to 16, I think it's right there. Okay.
Wasn't it the next 6?
For the next 16 hours, good. Yes. Over here to 24. Okay. Okay, now it's cold in here, Jordan. Could you turn that back up to 74? Yes, Ben.
So, why does it say the same like that instead of going up by 500 each hour?
Because this is pumping at a constant rate. That rate's not changing. It is pumping at a rate of 800 gallons per hour.
You're graphing the rate, not the.
Right, it's not a rate of change, right? So it's not increasing by 500 gallons per hour every hour. Because we're graphing the rate, we're not graphing, is that right? Wait a minute.
If we did 500 gallons every single hour, we wouldn't pay like that. Because now it's 280,000.
Your question got me confused. Hold on a second. I got to get my thought together here. Let's see. Removing water at a rate of 500 gallons per hour. Okay. Yeah, no, this is correct. Okay. So if we look at this, right, if we want to know how many total gallons were removed, okay, so if we want to know how many total gallons are removed in the first 8 hours, then it would be the 500 times 8. That's going to give me my total gallons of 4,000 gallons. Okay.
But on this, you're just graphing the rate and not graphing like an actual line.
Yeah,
guess, like an
I
actual
should change this. Rate of removal, because that's what we're actually graphing. Yes. Okay. And if I wanted to know how many gallons were removed in the next 16 hours, right? So we know if it's removing it at a rate of 900 gallons per hour for the next 16 hours, that's going to equal 14,400 gallons. I'm sorry, I labeled my axis wrong. The y-axis is the rate of removal in gallons of water. Okay. Does that make sense? Okay. So what we're looking at here is actually an integral. We're looking at the area, right? So we're looking at the area between the curve and the x-axis. Now, if we're talking about the rate of removal, right, that's, we can just call that d of g, right? D of g. This graph is the graph of d of g. If I integrate d of g, I get the area under the curve, which gives me just g, gives me the gallons. Okay? So what we're doing is we are integrating, okay? For now, we're going to start off, instead of learning the actual formula and the method of integrating, we're going to look at these Reimann sums, okay? And this helps us to conceptualize what's actually going on, okay? Reimann sum is basically, we start off with what we call the rectangular approximation. Sometimes you'll hear it said in that way instead of Reimann sum, right? Reimann sum, or in this case, rectangular approximation, okay? Sometimes we don't use rectangles, but right now we are. And the idea here is that if I have a curve, I can estimate the area under the curve by drawing rectangles. Okay, so if you look at this example here, we drew a whole bunch of rectangles. These are all inscribed rectangles. And if you notice in this example, the right edge of the rectangle is touching the curve. Okay, so if I was going to continue, it would be down here, right, and then there. Okay, so we see that we have this right edge touching the curve. That means we're going to call this a right rectangular approximation, or right Riemann sum. This is going to approximate the area under the curve. So let's work through this particular example. Okay, so this says consider a 30-gallon aquarium being filled with water at a rate modeled by R of t, okay, which is a sine function. R of t is in gallons per minute. Find the volume of water in the tank. Okay, so we're looking for how much water is in the tank, the total amount of water in the tank. So one of the reasons one of the reasons that this is helpful to look at it like this is that it makes sense when you're looking at it like this. You're like, okay, this I'm putting the water in here in gallons of water per hour, right? That's my rate. If I want to know how much is in there, I would take my rate of 500 times the 8 hours. Well, that's area. That's the area of this rectangle. If I wanted to know how much was in here, I would take the rate times the number of hours. Well, gee whiz, that's the area. If I have a graph that represents the rate, if the graph represents the rate, so if the graph represents the derivative, right, then the area under it is going to represent the total amount. Okay? So this graph is a graph of R of T, which is the rate at which the water is filling the tank, the aquarium. I want to know how much is in there. Find the volume of the water in the tank after 5 minutes. So I'm only going up to that blue rectangle there, okay? Each one is 1 minute wide. So what we're going to do is we're going to find the area of each rectangle. So the first rectangle has a width of 1 and a height of 2. The next rectangle has a width of 1. So they all have a width of 1 in this example. And the height is, right, we're looking where it intersects the curve. The height is 4. Plus 1 times, we're looking at the yellow one. Right there, the height is, looks like 5.5, 5.5. Plus 1, okay, it's intersecting the curve right here at 6. Plus 1 times, looks like maybe 5.75. Okay. Okay. Are we happy with that? Okay. That would be a great answer if I had to just estimate those Y values. Do I have to just estimate the Y values? Why not? Why not, Caitlin? Okay. So can someone explain to me what I actually did? Where did this come from? Came from the area of what? The rectangle. Okay, so where'd the 1 come from? The width of the rectangle. Where'd the 2 come from? The height. Right there? Is it 2? Well, what is it? What's the height? How do I find the height? It's definitely not 2. I can see it's not 2, right? Okay, what do we actually find? So this was the X value, right? So what's this? The Y value. I'm estimating. Do I need to estimate the Y value? Can I get an exact value for that Y value? No? Read the question again. The question says, the rate modeled by R of T equals 6 sine pi over 8. So can I get an exact value for the Y value? How would I do that? Yes, exactly. Right? So we have a function representing the Y value. No. So look, this is what we're going to do. Good question, right? So I've got T. My Y value is R of T, right? So then I'm going to just do area, right? So when my T is 1, what's R? 6 times the sine of pi over 8. And I'm just going to save us some time, and that's going to be, we're going to say that's equal to 2.296. So my area is 2.296. The next rectangle, when t is 2, it's going to be 6 times the sine of pi over 8 times 2, which comes out to 4.243. Okay, so the area of this curve, what's the area of this rectangle? What's the area of this rectangle? Is everybody with me? Come on, guys. Grow up here. Come on. Yeah. The area of that rectangle, 4.243. Right? So each rectangle, the next one, when t equals 3, it's going to be 6 times the sine of pi over 8 times 3, which is 5.543. Right? So I have to use that t equals 3 to find the correct y value, but the width is still only 1. So it's just going to be 5.543, right? I'm going to do that for t equals 4. When t equals 4, we end up with 6.000. Notice we're rounding it to 3 places. When t equals 5, we get 5.543, right? So I have to use the t in this particular problem in order to find the correct y value, or the correct r of t. The width of each rectangle is 1, so once I find that r of t, that's actually my area. I'm going to add all of these areas together. We're adding all of these areas together, and we get 23.625 gallons. Yes.
How come 3 and 5 line up, but they don't line up on the graph? Is that just because the graph is not right, or the math?
What do you mean they don't line up on the graph?
5 is.
Like
No, it does line up.
it carries the same value. It's like 5.
Well, it looks like 5 is
but
taller.
they don't.
Oh, I think that's just the limitations of putting the little rectangle on. That corner is actually right on the curve.
It
Yeah.
goes right.
Yeah. Okay. Okay. So we need to be careful, because what we did, right, we looked at the graph and we're like, okay, we came up with these y values. And I guess, to be fair, I kind of led you that way, right? But, right, just because we have a graph, we can't just look at the graph and estimate the values if we're given the actual function that generated those y values, right?
So what are those y values represent?
That's the height of the rectangle. Those y values are giving me the height of the rectangle. Okay? So I know the width of the rectangle, and then I know the height of the rectangle, so I can find the area of the rectangle, right? So that would be an approximation. Now, when I look at this area, right, that gives me an approximation of the area under the curve, right? The area under the curve, right? This is absolutely crucial that you understand this, right? The area under the curve is the volume. Yes.
I know we were talking about it when we said like the different rectangle.
Mm-hmm.
How it wouldn't give you the exact. But now looking at it, if it's like evenly like proportion like that, wouldn't they give you the exact?
Yeah, so all of these are going to be approximations. All those, depending on the shape, we might be able to get one that's equivalent to the exact.
Because this looks like it'd be the exact because they're not sticking out on the outside.
Because when you do the other side,
it would
yeah.
be inside.
Yeah. So the only way to get the exact every time is to actually take the integral, okay, which we haven't done yet, except for in our tutoring session, right? For now, we're approximating with the rectangles. So if I'm just approximating the volume from 0 to 5, these rectangles are going to give me an over approximation. Okay. Since this curve is symmetric, if I approximate it from 0 to 8, it's going to balance it out, and I will get an exact approximation. Okay. Again, we'll talk about. We'll just hold on to that thought for a couple minutes, okay? So what we just did is what we call a definite integral. So we integrated from 0 to 5. That's the symbol for integrating. We integrated from 0 to 5, and we integrated the function r of t dt. That gave us the volume of that curve, okay? That gave us the area under the curve. Okay, let's look at some other examples, right? Here are the 3 types of rectangular approximations. We have a left rectangular approximation, and when it's a concave down function, a left rectangular approximation is going to be an under approximation. If it's a concave up, then the left approximation will actually be, see if I can draw that now, will actually be an over approximation. Okay, a left approximation will be the over approximation. This is a right endpoint approximation, and we're talking about the upper corner of the rectangle. And then this is a mid rectangular approximation. Yes. Right.
So if it's concave up like that, are you not looking for what's inside, like above?
Yeah, good question. So remember, let's see if I can draw. Remember the integral, or the Reimann sums, is giving us the area between the curve and the x-axis, right? So if I were to draw left point rectangles, right? There's a left point, and then we have left point, right? So the left corner of the curve, right? And it's the area between the curve and the x-axis, okay? Okay. I don't want to do that yet. Okay, so let's look at example number 3. I don't want to look at the definition yet because that just makes it very confusing looking. Okay. Look at example 3. Find the area under the graph of f of x equals 1/2 x plus 1 on the interval from 0 to 5 using geometry. Well, so let's see. So I'm talking about.
Looks like the trapezoid.
Sure does look like trapezoid, doesn't it?
Yeah.
Well, I could do the rectangles, but it's going to give me an approximation, and that approximation will not be correct, right? It didn't say approximate. It said find the area. So this is one big, gigantic trapezoid, right? So a trapezoid, normally a trapezoid we picture looking like this, right? Here we got base 1, base 2, and this is the height. So what we're doing is we're going to look at that trapezoid, but we're going to kind of turn it on its side, right? Turn it on its side. But instead of having that line there, we just have the height. We don't have this part here, right? So there's my height right there. This is my height. This is my B1 and this is my B2. And it doesn't matter what order we put the B1 and B2. The area of a trapezoid is 1/2 the height times B1 plus B2. You are expected to know that. Okay. So if I want to find the area of this, since this is a linear function, I do not have to break it into subintervals. I can just work with it as one big gigantic trapezoid. So the area will be 1/2. What's the height of this trapezoid? 5. 1/2 times 5 times B1. What's B1? 1 plus B2, which is, okay, so where do we have a problem, right? What do we have to do? We're doing the same thing again, aren't we? Got to plug it in, right? See, be careful, right? Our tendency is to look at the graph, but we have an exact value. Y is equal to 1/2 times 5 plus 1, which is 3.5. Yes, ma'am.
Why isn't it 6 if it goes past the 5?
Because it said to find the interval from 0 to 5.
Oh, okay. That's fair. I was getting that.
Yes, Faith.
Where are we getting 1 from for B1?
If I plug in 0, right, because x is 0 right here. If I plug in 0, 1/2 times 0 plus 1 is 1.
Wait, why is it 0? Because doesn't it go to... Wait, what is B1 in that instance? Phase 1, the bottom.
Okay. Let me. It's the trapezoid turned on its side, okay? So the B1 and the B2 are referring to the height, and the height on an XY graph is the Y value. Oops, sorry. The height on the XY graph is the Y value. Okay? So we take the X value, and it said to do it on the interval from 0 to 5. So when X is 0, Y is equal to 1/2 times 0 plus 1. That comes from this function, which is 1. So that's B1. B2 is when X is 5, and Y will be 1/2 times 5 plus 1, which is 3.5. Okay? That's where I get the B1 and the B2.
But wouldn't it be 1, not 0?
Why would it be 1? 0, 1 rather.
Because you're taking the height of it and it goes up to 1, not 0.
When X is 0, Y is 1, right? That's my B1. That means this trapezoid has a B1 height of 1. When X is 5, Y is 3.5. That's my B2. Okay. So we've got 1/2 times 5 times 4.5, which equals 45 over 4, or 11.25 square units. Units squared. Okay. Okay, so we took this and we turned it into one big gigantic trapezoid. And here's my B1, and here's my B2, and this is my height. When we do these trapezoids, we're always turning that trapezoid on its side. So the height is always going to be the X value with a change in X. Okay. Okay, let me just go through this again because we talked about it, but let's make sure we look at it more specifically. Okay. For the function shown, draw rectangles forming the left-hand sum shaded in blue. Calculate the left-hand sum where delta x equals 2. Okay, so what we're doing is we're going to draw rectangles that have a width of 2. That's what delta x is, the change in the x value. So my rectangle has a width of 2. So here's one rectangle here that has a width of 2. And then we'll have another rectangle right here. It has a width of 2. And then here's a third rectangle right there. Okay? So we're going to draw those rectangles. It wants it to be a left Riemann sum. So when I draw my rectangle, the left edge has to come in contact with the curve. So there's the left edge, right? It has a width of 2. So there's my first rectangle. The left edge comes in contact with the curve. Okay, our next one is going to start here at 2. It has a width of 2, and the left edge has to come in contact with the curve. So it looks like that. Okay, see how the left edge of the left corner comes in contact with the curve. And then my third rectangle, right here, again, it has a width of 2. The left corner comes in contact with the curve. Okay. I know that they have a width of 2 because it said delta x is 2. Delta x refers to the change in the x value. So it has a change in the x value of 2. Okay. So the area that I'm calculating here, okay, it says to shade it in blue. So this is the area that I'm actually calculating, this shaded in blue space. Okay. Calculate the left-hand sum. Okay, let's do that. All right, so we're going to take the area of each rectangle. So it's a length times a width. So the first rectangle has a width of 2. And what's its height? 8. The second rectangle has a width of 2. And what's its height? 7. And this time we don't actually have an equation, so we do have to estimate. So it looks like it's a 7 on the graph. Plus 2 times, that looks like a 5. Okay. Now, a shortcut that you can make, if all the rectangles have the same width, you can just do 2 times and then put the heights inside because they're all being multiplied by 2. Okay. So let's see, this ends up being 40 units squared. Okay.
This is when you're finding the.
We're finding the area under the curve. Okay. Okay. Is this an over or an underestimation of the actual area? Overestimation, yes. If I can spell estimate.
Excuse me, Ms. Murray.
Yes.
Hi there, can I please have Sophia Loretta to the front office for a moment?
Okay.
Thank you.
Okay. Let's look at the next one. Draw rectangles that represent the right hand approximation. I'm going to erase this so that it doesn't look so messy. Okay. Okay. We're still using delta x equals 2. So this time we're looking at a right approximation. So I'm going to take my right edge and go up until it intersects with the curve. Okay. So it's going to look like this. Take the right edge until it intersects with the curve. So there's my rectangles. Okay. And this time we are shading it in red. Okay. Okay. And let's calculate that area. So each rectangle has a width of 2, so I'm just going to factor the 2 out. Okay, so let's look at our heights. We've got 7 plus 5 plus 1, which equals 26 units squared. Is that an over or an underestimation? Underestimation, yes. Okay.
Can't you find like what the actual one would be right comparing both?
Say that again.
Could you find what the actual answer is?
Well, we don't have an actual equation for that curve, so in this case we can't. We could get a better approximation by using what we call the midpoint approximation. Okay, so this is what the midpoint approximation, oops, I didn't mean to erase those. This is what the midpoint approximation would look like. Let's see. Okay, whoops, try that again. Okay, so we would take our curve so that the mid part of the rectangle intersected.
Why can't we just like do like between 40 and 26 is a 14 difference? So then you do add 7 or subtract 7, you get 33.
If you've already done the left and the right approximation, yes, you can do that.
That would be the exact one.
Right, correct. Let's see, looks like maybe right about there. Yes, you could take the average between the two and get the mid, right? Or if you don't have those approximations and you're just asked to find the midpoint approximation, right? Drawing the rectangles really helps, right? So let me just do this down here. We still have each rectangle has a width of 2, but now let's look at the height. So now the height is coming from the point in the middle of the rectangle. So it would be where x equals 1. So this looks like maybe, we'll just say 7.5. And here we're looking between 2 and 4, so at 3. And that looks like it's maybe 6.25. And here we would use x equals 5, which looks like it's 3. So when we do the midpoint approximation, we find the midpoint of the rectangle, of the width of the rectangle, and then figure out the y value from that. That gives us the midpoint approximation. What does this come out to? We did a pretty rough approximation there, but 33.5. So 66 divided by 2 is 33, so yeah. Okay. Okay. All right. This is helpful if we have a concave up function and we look at the left approximation. Did we do a concave up? Concave up left approximation, is that going to be an under or an overestimate? Underestimate. Okay. If it's an increasing function. If it's a decreasing function, it'll be an overestimation. Right? So if I'm going up like this, it's an underestimation. If I'm going like this, it's an overestimation. Okay? If it is the right-hand approximation, then we will have an overestimation and an underestimation. You can kind of reason it through. Just draw a little, that's what I do. I just draw a little curve here and look at it. Okay? Concave down and increasing, so we're looking at this. Left approximation will be an under, and the right approximation will be over. concave down and decreasing, so we're looking at that. A left approximation will be over, and a right approximation will be under. Okay. Okay, do I have time left? Oh, yeah. Okay. So these are probably the most common types of questions on your AP exam involving Reimann sums. Okay. When they give you a table. So the table represents the velocity in feet per second of a car traveling on a straight road over a 50-second interval. So this is velocity, right? And then this is time over here. Okay. We want to estimate the distance of the car traveled during this interval using the right and the left hand. Okay. Remember, right, velocity. Okay. Remember the integral. How did the integral and the derivative relate? They're opposites, right? The integral is the antiderivative. So if I have to take the derivative of a position function to get velocity, then if I integrate velocity, I get the distance. Okay? So the integral of velocity is the distance. The area under the curves that we're doing, these are all finding the integral. Okay?
So if it's S of t, the integral would be v of t, and if it's v of t, the integral is just t.
No. If it's v of t, the integral is s of t. You can't take the s of the integral
I
of
was
it.
thinking of a of t.
Right. Okay. Estimate the total distance traveled by the car using the left-hand sum approximation with 5 partitions of equal length. Okay. Well, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If I start at 0, 0, right? 5 of equal length. So it looks like, right, if I have one rectangle, 2 rectangles, 3 rectangles, 4 rectangles, 5 rectangles. That's what I usually do on the AP exam instead of drawing out the graph. Okay, but the graph does help, but of course it takes a lot of time. Okay, so there's my 5 rectangles. So each rectangle, do they have the same width? Going 0 to 10, I'm going 10 to 20, 20 to 30, 30 to 40, 40 to 50. Yes, they do. So the width is 10. So I'm going to do 10 like that. Okay. I can do each separate rectangle, but I don't have to. Okay. We're looking at the left hand sum. The left sum. So that means when I look at my rectangle, I'm looking at the left sum of that rectangle. So what's the y value for the left-hand side of that rectangle? 0. Okay, that's the first rectangle. I'll do each rectangle separately. The second rectangle has a width of 10, right? And we're looking right here. What's the y value of that rectangle? 20. Everybody following me? Okay. Let's look at it on the graph. Okay. Let's look at it on the graph. 0 to 10, and we're doing the left Riemann. So that first rectangle is actually just right here. This is the first rectangle down here. It has a height of 0. The next rectangle is right here. And then the next one is here. And then we have another rectangle here. And then the last rectangle is going to be right here. Okay. Those are the rectangles. If we look at it on the graph, maybe it helps, okay? But I'm just drawing the rectangles Yes, Ben.
What happens if a rectangle kind of goes over 2 points?
It won't, because when we're looking at the height of the rectangle, we're always referring to the y value that corresponds to that x value, right? So here was my first rectangle right here. That was my first rectangle, okay? And then here's my second rectangle, right here. Oops. Right, there's my second rectangle. And my third rectangle is right here. Right, there's my third rectangle. So it's got a width of 10 again. What's the height of that third rectangle? It's a left-hand rectangle, so I'm looking at the left side of the rectangle, so it is 52. Right? Plus, the next rectangle also has a width of 10. What's the height of that rectangle? We're looking at the left side of the rectangle, so that has a height of 80. Plus, the last rectangle has a width of 10, and this time it has a height of 77. Everybody following that? Okay. When we add that all together, we get 2,290. Now let's look at the unit, okay? We can reason through the unit, but we can also do a little unit analysis. Okay? If we look at this, we're taking the 10, right? The 10 comes from there, from the t value, which is seconds. So we're taking seconds and we're multiplying it by the height, which is the y value, which is feet per second. So what unit am I left with? Feet. Okay. We could reason that through because we know that when we integrate the velocity, we get distance, and distance is going to be in feet. Okay. Okay. Show your setup and draw the rectangles in the graph in blue. Okay, I'm not going to worry about that right now. Use the right sum. Okay, so I'm just going to draw my rectangles back up here again. Oops. Okay. There's one rectangle right there. And there's the next rectangle. And here's a third one. And the fourth one. Wait a minute, what'd I do? Oh, gee whiz. That was so dumb. Oy vey. Oy vey, oy vey, oy vey. Oy vey. Did it like this. Okay. Okay, so we're looking at the right Riemann sum this time. So let me just draw some little lines in there. Okay, so we're looking from 0 to 10. But the right edge of the rectangle is going to come in contact with the curve. So I'm going up I start at 30. I go up until the right edge of the rectangle comes in contact with the curve. Okay, so now we're looking at these rectangles. Okay. All right, so we've got a width of 10. When I'm looking for the height, this time I'm looking where t is 10, so the height is 20. And the next one, 10 times a height of 52 plus 10 times, what's the height on this one? Okay. Plus 10 times a height of 77 plus 10 times a height of 74. Notice from the table, when we did the left Reimann sums, right? The left Reimann sums, we went with our rectangle at 0, right? Basically, our rectangles went like this, ending on the 70, okay? With the right Reimann sums, everything is shifted over. This time we're ending on the 74. Okay, and when we do this, we get 3,030 feet. Okay. Okay, midpoint approximations. I'm going to do this one a little bit slower with you. Okay, midpoint approximations. Let's look at our rectangles. So the middle of the rectangle comes in contact with the curve. Okay, the middle of the rectangle is crossing the curve. Okay, there's my midpoint approximation. Okay, so if we look at our table, okay, again, the width is 10. So 10 times, when I'm looking for the y value, I'm going to the middle. So the rectangle has a width of 10, so I'm looking for this y value. Okay, 0 to 10. Okay, so my y value is what? 14. Okay, the next one, 10. So I'm going from 10 to 20. So the x value that I look at, or the t value, is 15, which means I'm using a y value of 28. Right, between 20 and 30, I'm using the midpoint, so 25. So we're using a y value of 70 plus 30 to 40, so I'm looking at 86. And then the last one is using 45, so it's 70. And we get 2,680. Okay. Is that the average of our left and right hand? No, it's close, but not exactly. Okay. Right. If it's symmetrical, it will be. Okay, trapezoid. So we're gonna stop there. For homework, I'd like you to do part D and E. Yes. Yeah. For homework, I want you to do part D and E. Okay.
What is the trapezoid? I don't understand. Like when you do like the left one, mine like line up with the right one.
When I'm doing the left one?
Yeah.
But no.
Like, cause I had everything right until I got to like 30 to 40 and 40 to 50.
Okay, there's my left one, okay? So when you're using the left one, right? So if you're talking about this rectangle right here, the left side we would be using the t value of 30 to find the y value, to find the height. So what it's doing is telling us which t value we're using to find the height. So here we're using 0. This rectangle, we're using t equals 10, so we're using the height of 20. In this rectangle, we're using t equals 20, so we're looking at a height of whatever that is, 52. Okay.
I see where it's different, like that angle. Because like the rectangles look similar, but like
It's where the y value is. Yeah.
Okay.
Okay. Other questions?
I have a question. You have a homework 6.1 and Google Classroom. Do we have to do that? It says.
I'm going to change that. Thank you for showing me. Thank you. You're just going to do these two.